Hello friends, this is Animesh and welcome to the Gate Mantra. So in this video we are going to see our fourth case. Okay, in the last video we have covered our first three cases. Okay, so if you have not attended our last video, or you have not seen our last video, please go through it, because before understanding that last video you will not able to understand this video, right? So in this video we are going to start with the our fourth case. Okay, our fourth case. Okay, so I am assuming the case number fourth here. So in the case number fourth, what we are going to do, first make the connection, right? What we are doing from the beginning, we are connecting this source, okay, to the body, and we are keeping this body to the ground. Why to the ground, or why to the lowest voltage among all the four terminal? Because we don't want this diode that's present here, okay, will be in forward bias, because if once it will be in the forward bias, a large amount of the current will be passed through it and our MOSFET will be burned out, right? That's why we want this diode that presenting here in the depletion region. Okay, we want this diode to be in reverse bias. Okay, that present here, right? So here what I am doing, we are giving a case force that first we are assuming, okay, the VGS we have applied greater than the VT naught. What is VT naught? The threshold voltage. Why we are applying the VGS is greater than VT naught? Because we have created the channel here. Here the large amount of the electron is presented. So when our gate to source voltage is greater than the threshold voltage, in this case the large amount of the electron, okay, the large amount of electron is present here. Large amount of electron is presented here, right? Now what we are doing, see what we are doing, we are applying this voltage, okay, across this, okay, we are applying drain to source voltage. So what we are doing, we are applying VDS, and we are increasing this VDS by a small amount. We are increasing this VDS, okay, VDS till 50 millivolt, means very small amount. We are increasing this VDS by a very small amount. So once we applied VDS, so let's me make the connection here. Okay, what doing, I am applying the VDS here, which is greater than the VT, to create the channel. Okay, and I am applying the VDS here, okay, a very small drain to source voltage, right? So here VGS applying greater than VT naught, and here I am applying VDS, and I am increasing this VDS by a small amount. Okay, so let me connect this to the source for better clarification. Let me connect this to the source. Okay, so this is the VDS. Okay, this is the VDS positive terminal. Okay, connected to the positive terminal is connected to the drain, and the negative terminal is connected. The positive terminal is connected to the drain, and the negative terminal is connected to the source. Okay, and we are increasing this VDS. We are increasing this VDS less than 50 millivolt. Okay, or till 50 millivolt by a small amount. So what will happen when we are increasing this VDS? Okay, when we have applying this VDS by a very less amount, okay, by a very less voltage we are applying here, millivolt in millivolt, 50 millivolt less than, then the electric field, okay, this is the positive and this is the negative, the electric field is present like this, from positive to negative. Okay, and the electron that presented in the channel, this electron that presented in the channel is attracted, okay, or is feel the electric field, okay, is will feel the electric field, and it will be start moving toward this, okay, toward this, it will be start moving toward this. Okay, so see here, the electron will be start moving like this. Okay, so electron will be move toward this, right? Okay, so what we can say here, okay, when we are increasing the VDS by the small amount, okay, the when we are increasing the VDS by the small amount, okay, the channel is uniform here. First thing to know, channel is uniform here, and the two things happen here, right? The two things happen here. The first one, okay, we know that I, what will the value of the current, then I will be equal to, let me give this, okay, in the next page. I copy this in the next page. Let me delete this to delete because I need more space, right? So see here, as we know that the current I, as we know that the current I will be equal to the, this current I will be equal to the N, okay, the concentration of the electron, NQ, the charge of the electron, nu, and the mobility of the electron, and this is the electric field, this is the area. This electric field is nothing but minus VDS divided by L. L is the length of the channel. What will be the L? L will be the length of the channel, right? Length will be the length of the channel, right? Okay, so here two things happen. First, when we increase the VGS, okay, the concentration of the electron in the channel will increase, the concentration of the electron in the channel will increase, and hence the current is increased, this ID current, okay, this ID current will be in opposite direction to the flow of the electron, and this will be like this. This is the ID. Drain current, the drain to source current is increased, or we can say IDS will increase. Okay, now our second case is when the VDS is increasing. Okay, when the VDS is increasing, what happened? See what happened when the VDS is increasing by the small amount. What happened? The electric field is increasing. Okay, because electric field equal to VDS by L, as VDS by L. Okay, electric field is increasing, and due to this again the current, ID current, is increasing. So we have seen here the ID, the drain current, is the function of both the VGS and the VDS, okay, the VGS and the VDS. And we can also say that, okay, in this, when we have applied the drain voltage, okay, the drain voltage a very little amount, we have applied the very little drain voltage, okay, the drain current, okay, is increasing linearly with applying this VDS, okay, at a constant gate voltage, okay, at constant. And see here we have kept VDS constant here, okay, and here we have kept VGS constant. So at constant VGS, okay, at constant VGS we have seen that the ID is directly proportional to VDS, okay. So when we draw a, okay, when we draw a graph, okay, between this ID and the VDS at a constant VGS, okay, this is VDS and this is ID, drain current. So we will found that. Now let's me draw this voltage, okay, 50 millivolt. This is the 50 millivolt here. Now what happened, okay, what happened, okay, first I am drawing this. See here, first let me draw, then I will explain. Okay, so here we have drawn this line, okay, this line, this for the VGS equal to VT plus 0.5 volt. We have drawn this VGS equal to VT plus 1 volt, okay, we can write like this, 1 volt. This is for VGS equal to VT, in the VT not threshold voltage, plus 1.5 volt, okay. So as we have seen, at a constant VGS, okay, at a constant VGS, when the VGS will be equal to the VT naught plus 0.5, as we increase the drain to source voltage, the drain current will increasing, okay, at a constant VGS, okay, when we increase the drain to source voltage, the drain to source current is increasing, right. Now see again, at a constant VDS here, at a constant VDS, this will be equal to the 50 millivolt. As we increase, okay, as we increase at a constant VDS, as we increase the VGS, the ID current will be increases, okay, means here the ID current will be different, here the ID current will be different, and here the ID current, drain current will be different, okay, drain current. So here the two things we have to understand, at a constant VGS, when we increasing the VDS, the drain current increasing, and at a constant VDS, when we increasing the VGS, the drain current is increasing here, okay, right. And we can see also here, this is, let's see this, this is the ID3, is the ID2, this is the ID1. Here we can say ID3 is greater than ID drain current 2 is greater than drain current 1, okay, right. So what we have seen what happened when we increase the drain current by a very small amount, right, by a very small amount, it's about the 50 millivolt we have assumed, okay. Now we will see what happened when we increase the drain voltage, okay, by a large amount, okay. Now let's see what happened when we increase the drain voltage by a large amount. So First we have seen here. Now one things here we have to know. Okay, here's one things we have to know: the overdrive voltage. What is the overdrive voltage? Or we can also say this is the excess voltage. Overdrive voltage, excess voltage, okay, or the effective voltage. So what is this? What is this? This overdrive voltage or excess voltage or the effective voltage is the voltage that applied at the gate terminal, okay, above the threshold voltage. So we can say VGS minus VT naught will be equal to the overdrive voltage, okay, or the excess voltage or the effective voltage. So this is the voltage applied at the gate terminal, okay, beyond or above the threshold voltage is known as the overdrive voltage. So here we have seen what we have applied. We applied VGS minus VT naught equal to 0.5. So here we can say overdrive voltage is 0.5. Here VOV equal to VGS minus VT naught is equal to 1 volt. And here VOV, that is VGS minus VT naught, will equal 1.54. So here we have seen this is the extra voltage that we applied at the gate terminal beyond the threshold voltage, okay, right. Now let's see, when we increase the drain voltage by a large amount, what happened? Okay, okay, now let's see here, when we increase, let me another keep this copy, okay, future, okay. Now what we are doing here, the case number fifth, what we are doing here, we have kept VGS is greater than VT naught, and what we are doing, we are increasing VDS beyond 50 millivolt, okay, we are increasing VDS by the large amount. So we have done, and now we are doing the connection, okay. So from the beginning we have connected this source terminal to the body terminal, okay, and we are making this body ground, right. Now we have applied this get to source voltage, okay, this is the VGS, okay. Now we apply drain to the source voltage, okay, this is the VGS, right. So let me write the name, this is the VGS, it's T naught, and this is the VDS, okay. Now what we are doing, we are increasing the drain voltage, okay, we are increasing the drain voltage by the large amount. So as we have seen here, and the VGS is greater than VT naught, so large amount of the, so the large amount of, okay, large amount of electron or the channel has been created, okay, when the VGS is greater than VT naught, the channel is created already. So let's make the channel N type channel, okay, yeah, or N channel, okay, right. Now when the VDS, when the drain voltage is less than the 50 millivolt, okay, or when the drain voltage is increasing by the small amount, right, is increased by the small amount initially, when the drain voltage is increased by the small amount, right, the channel is uniform here, the channel was uniform here when the drain voltage increased by the small amount. Now when we are increasing the drain voltage, when we are increasing the drain voltage by the large amount, then listen me carefully here, when we are increasing the drain voltage by the large amount, then the voltage between the gate and the channel, the voltage between the gate and the channel is not equal, okay, is not equal when we are moving from source into the drain in. Means when we are increasing the drain voltage, okay, when we are increasing the drain voltage, the voltage between the gate and the channel is decreasing when we are moving from source to drain, when we are moving from source to drain. So the voltage at the source end, okay, the voltage at source end, voltage at source end, okay, between gate to channel is VGS, and this is the reference voltage. And as we are moving from source to the drain, the gate to the channel voltage is decreasing, and the voltage at drain end is VGD. This will be the equal to VGD will be equal to the VGS minus VDS. Okay. Now, when we increasing the drain current, the channel will be non-uniform. The channel will be non-uniform. Why? As we know that the charge density or the free electron density, okay, of, okay, the charge density or the free electron, okay, the charge density in the channel is Qi, and Qi will be equal to minus Cox, okay, into VGS minus Vc of Y. This is the voltage of the channel, minus Vt naught. This is the threshold voltage. Okay. Now at, okay, now as we are increasing, as now as the gate to the drain voltage, okay, the gate to the channel voltage, okay, the gate to the channel voltage is decreasing when we are moving from drain to the source, okay, the depth of the channel, okay, the depth of the channel or the charge, the depth of the channel or the charge is decreasing, okay, is decreasing as we are moving from source to the drain end. Okay, listen carefully. When we are moving from source to the drain end, the channel to the the gate to the channel voltage is decreasing, and along with this, the depth of the channel is also decreasing as we are moving from source to the drain end, because the depth of the channel is proportional to the gate to channel voltage. Okay, so so at so so when this VGD, okay, or when this VGD get to the drain voltage is, when this VGD is, okay, greater to the Vt naught, is greater to the Vt naught, okay, this region of operation is called the linear region, linear region of the operation. And in this region, okay, the the channel, okay, the channel that was present here initially, this channel, okay, this channel is become tapered, because this channel is become tapered, okay, this channel will be become tapered, okay, like this. Why? Because the gate to the channel voltage is decreasing as we are moving from source to drain, and due to the depth of the channel, okay, or the charge that present in the or the electron concentration that present in the channel is decreasing as we are moving from source to drain. So when we increase the drain voltage more and the more, the channel become more and the more tapered in the shape, okay, like this, okay. Initially this was the channel, now this is the channel, and again the channel, the depth of the channel is decreasing at the drain end. And when when this VGD, when this VGD will be equal to the VT naught, okay, then the pinch off occur, then the pinch off occur at draining. So what is the pinch off? When the VGD will be equal to the threshold voltage, the depth of the channel at the drain end become zero. Let's see how. So when this VGD will be equal to VT naught, the pinch off occur. What is the pinch off? Pinch off is nothing but the depth of the channel at the drain end will become zero, okay. So this VGD, as we know that this VGD, okay, as we know that, we will write in the next page, okay. This VGD is equal to the VGS minus VDS, and when it will be equal to the VT naught, okay, then this VDS will be equal to the VGS minus VT naught, okay, and this voltage, okay, this voltage is known as the VD set. This voltage is known as the VD set, okay. So as we can say that when the VDS will be equal to VD set, the pinch off occur at the drain end, okay. The pinch off occur, or we can say that the depth of channel is zero at drain end, right. As we have seen, the free electron, okay, the free electron density, okay, charge of the free electron will be this in the channel, okay. So as we have seen, Qi of y, okay, is Qi of y is equal to the minus Cox, okay, Vgs minus Vc of y minus Vt naught, okay. Now we are going to keep this equation, okay. Now minus Cox, okay, Vgs, okay, minus Vc of y. What is the Vcy? Vgs minus Vt naught, okay. We are keeping this, okay, at Vgs minus Vt naught, or minus Vt naught, okay. Now on doing this, the Vgs minus Vgs plus Vt naught minus Vt naught, okay, then Vt naught cancel, Vgs will be cancelled. Now the charge density in the channel at the draining is 0. So from here we have proved that when our VGD will be equal to the threshold voltage, that is the VT naught, okay, and this condition, when the and from this condition we have derived the VDS will be equal to the VGS minus VT naught, or we can say this VDS is the VD set, this voltage, the charge, okay, or the electron, or we can say the channel depth, okay, the depth of the channel at the draining is 0, okay, is 0, right. And why we have kept here the VD set? Because the voltage at the drain in, okay, is equal to the VD set. This is equal to the VGS minus VT naught, okay. right, as we have kept the source as a reference voltage, right. So we have seen in this figure that the channel depth at the drain is 0, and this is called the pinch off. This is called the pinch off. Okay. So here when we are increasing the VDS, okay, drain voltage, the free electron that present in the channel, okay, the free electron that present in the channel will find the more resistance, okay, more resistance, because the depth of the channel is decreasing, or the channel become non-uniform, or we can say that channel become tapered. Due to the tapered size of the channel, the resistance of the channel is increasing, okay, the resistance of channel is increasing, and hence conductivity of channel is decreasing. And because of this, the drain current is decreasing, and due to this we will see the bend in the IDVDS characteristics, the bend of in the IDVDS characteristics. So when we increase the VDS, okay, when we increase the VDS from VD set, okay, theoretically, please listen here carefully, if we increase the drain to source voltage greater than the VDS, okay, then theoretically, okay, the size of the channel will not change, means the pinch off will occur at the drain end, but the shape of the channel, okay, the shape of the not size, the shape of the channel, okay, the shape of the channel is not changed, it will be tapered, okay, it will be tapered, and pinch off occur at the drain end theoretically. So I am not practical, this is not the practical case, okay, this is not the practical case. The practical case we will see in the channel length modulation, okay, topic. Here we see that when the VDS is increasing beyond the VD set, okay, beyond the VD set, okay, the the okay, uh, the channel size, the channel shape will not change, okay, and channel will be remain tapered, okay, and when we increase, okay, when we increase VDS beyond VD set, okay, the channel shape will not change, this is the theoretical, not practically, theoretically, okay. And this region of the operation, okay, and this region of the operation, okay, before this I want to add one two or more point, okay, so 1 2 point. So when we are increasing VDS beyond the VD set, the channel shape will not change, okay, but the free electron that are present in the channel will find the more and more electric field, okay, will find the more and the more electric field due to increasing in the electric field. Because of increasing the VDS, the velocity of the electron that present in the channel will be equal to the drift velocity limit, will be equal to the drift velocity limit. And theoretically we can say the velocity of the, okay, velocity of the electron is saturated, and hence theoretically we can say the drain current, okay, the drain current is saturated, theoretically, okay, saturated, and hence this region of the operation is called as the saturation region. Okay, when the VDS is greater than VD set, then this region of the operation is called as the saturation region, right? Saturation region. And what was this region? Earlier, this region was the linear region. So in linear region, as the VDS is changing, okay, as the VDS is changing at a constant VGS, okay, the drain current changing up to only 50 millivolt. After we applied the VDS beyond the 50 millivolt, we have assumed the 50 millivolt, or we can say by the small amount. So when we increase the VDS by a large amount, okay, we will see the bend in the, okay, ID VDS characteristics, and this is because of the increasing the channel resistance. So we can say that in the linear region, okay, the MOSFET is behaving like a voltage control voltage control, okay, resistor and this resistor of the channel RCS is controlled by the VGS, okay, gate to source voltage, right, in the linear region. And in the saturation region, as we have seen that it is acting like a constant current source, right? So here we have seen all the 5 cases, okay, related to the working of the enhancement type MOSFET. Okay, if you are not feeling it, okay, easy, then please go through this video once again, because the way I have explained it, okay, it's now become very easy to understand. Okay, I have covered all the, okay, small, okay, the point here, and I think it should be crystal clear for you. Okay, it should be crystal clear for you. Okay, I have explained all the small point here, okay, in the better way, right? So here we can say, okay, in cutoff region, in cutoff region when will the cutoff region will exist? When VGS is less than the VT naught, okay, the MOSFET is used as a off switch. Okay, in linear region, the condition for the linear region is VDS is less than VGS minus VT naught, okay, or we have seen that the linear region, this is the condition for the linear region. So if we expand this, okay, here the VGD, okay, here is the VGD, not the V. No, this was our condition, okay, for case 5. Okay, this was the condition, our condition for case 5. Okay, this was the condition, right? We seen here linear region, okay, linear region. So when we expand this, okay, VGD, then VGD equal to VGS minus VDS is greater than VT naught. If we expand this, then we have seen that VDS is less than VGS minus VT naught, okay, right? So this is the condition, okay, voltage condition for the linear region operation. So for the linear region operation, we can say this VDS is less than VGS minus VT naught, or we can say that VGD is greater than VT naught, okay, and this, and the one more voltage condition is that channel formation should be necessary, so VGS is greater than VT, okay, and in this region we have seen the MOSFET behaving like a voltage control resistor, okay, voltage control resistor, and its resistors is and its resistance is controlled by the get to the source voltage. So we can say voltage control resistor or voltage variable resistor. Now our third region of operation is the saturation region. So in saturation region, okay, the condition is the VGS is greater than VT not because for the channel formation this is required, and our second condition is VGD is here again VGD. Here VGD should be less than VT naught. If we expand this, we will get VDS. We will see the VDS is greater than equal to VGS VT naught, right? So in saturation region we have seen this is act like a constant current source, and in saturation region we use, okay, the Mosfet as a amplifier. As a amplifier, right? So we have seen the three region of operation for the Mosfet. First one is cutoff region, second is linear, and the third is saturation region, right? Now we are going to see the current equation. Okay, so here we are going to see the current equation. So here we are going to see first for the N MOSFET, for the N channel MOSFET. We can say N channel MOSFET or P type MOSFET because its substrate is P type, or we can say this NMOS, right? So in cutoff region, the derivation of this, okay, equation, current equation, will not ask in the gate examination. So I don't think it is necessary to derive the expression for the current equation, right? So in cutoff region, the voltage condition VGS is less than VT naught, and here the current will not flow because the channel formation is not here, because the channel is not exist here. So in cutoff region, our first region of operation, and our second region of operation is linear region. So for linear region, VGS must be greater than VT naught and the VDS less than equal to VGS minus VT naught, and the current equation will be ID will be equal to the nu n COX W by L, okay, and here VGS minus VT naught, okay, into VDS minus VDS square divided by 2, right? Now let's talk about the saturation region. Our third region of operation is saturation region. So in saturation region, what will be the voltage condition? VGS must be greater than VT naught, and VDS must be greater than equal to VGS minus VT naught. Okay, here the drain current equation will be 1 by 2 nu n, where nu n is the mobility, okay, COX is the oxide capacitance per unit area, and W is the width of the channel or width of the gate, and L will the length of the channel, and here we will VGS minus VT naught whole square. The derivation of this equation is not necessary, not at all necessary for the gate examination. Okay, so the derivation will not ask in the gate. The gate examination is a numerical type exam. So derivation will be not asked here. Okay, here now we are going to see the ID-VDS waveform that we have drawn here. This is for the small value of the VDS, Now when we keep the large value of the VDS, we will see what happened to the drain current that we have explained here. When we increase the VDS by the large amount, there is a bend in the ID. There is a bend in the ID VDS characteristics curve. Okay, because the channel resistance is increasing and hence the conductivity of the channel is decreasing. Okay, that's why the drain current is decreasing, right? And in the saturation, we have seen the velocity of the electron is saturated. Because of that, the drain current is saturated. Okay, this is the theoretical, not the practical. Okay, practically we will see the practical case in the channel length modulation, right? So I am drawing here the IDS VDS curve, and this will be the last topic for our today class. Okay, so I am writing here, this is the V, sorry, not V, this is the IDS, or we can say ID drain current, and this is with the VDS, drain to source voltage. Okay, and we are drawing this for the constant VGS. Okay, we are drawing this for the only one VGS. Okay, at a constant VGS means VGS not, or we can say any. So I am drawing here, let's see, for the small value of the VDS. Okay, for the small value of the VDS, this ID will be increase linearly. This is for the small value of the VDS. Okay, as we increase the VDS, right? As we increase the VDS, okay. Now see how this curve. If we increase the, now when we increase the VDS, this is almost constant. This is okay. For VGS equal to, I am using VT not 1 volt. Okay, or we can say 0.5 volt or 0.6 volt, because in our case the VT not A was 0.6 volt. Okay? So beyond 0.6 volt we are applying the 0.5. Okay, so now what we need to see, this for the small value of the VDS. Okay, our current is increasing linearly with the VDS. Now here beyond this, okay, beyond this we can say, beyond this, okay, we can say the drain current is bending. Okay, at this point we can say the drain current is bending, and beyond this we can say, okay, not this, on this, okay, we can say beyond this the drain current is constant. Okay, beyond this the drain current is constant. So we can say this is the VDS set, this is the VD set. Okay, and it will be equal to the VGS minus VT naught. Okay, so this is the region where the VDS is less than VGS minus VT naught. Okay, okay, this is the region. So this is the linear region of operation, linear region, or we can say pivot region, and this is the saturation region of operation. And when the VGS is less than the VT naught, okay, we can say this. Okay, we can draw another, we can, or we can see this is for the cutoff region when the VGS is less than VT naught. Okay, so this is the linear region, this is the saturation region, and this is the cutoff region. So in saturation region the current is saturated because the electron, the free electron, okay, that present in the channel, okay, experience the large amount of the electric field because of increasing VDS, okay, because of increasing VDS beyond VD set, and hence it gets saturated. Okay, and here the graph is bending because of the increasing resistance, because of the increasing resistance in of the channel. Okay, because of increasing the drain to source voltage. Okay, right. So this is the curve, this is the curve. Okay, this is curve for the drain to the drain to the drain to source voltage, drain current and the drain to source voltage. Okay, this is a curve for a constant VGS. We have kept this VGS equal to VT plus 0.5 volt. Okay, right. So this is the ID VDS characteristics curve. Okay, right. So in the next lecture we are going to see the channel length modulation. It is the practical, okay, practical case when we have seen here that theoretically the channel shape will not change, okay, when VD is greater than VDS, but in the channel length modulation we will see how when we increase the VDS beyond the VD set, the how the channel shape will be changed and how the effective length of channel will be changed, right? So in this video, okay, we are going to India. Okay, in next video we are going to see the channel length modulation, right? So thank you for listening. Okay, thank you very much.